Swayam Prabha. Digital India. Educated India.
Good morning. So in the last class, I was talking about morphology, microstructure of polymers. We saw that polymers may actually exist in amorphous structure, or it can also form some semi-crystalline structure. And if you look at crystalline polymer, semi-crystalline polymer, the chains, the long molecular chains pack themselves into a small lamellae, which forms like more like a thin plate like structure of the order of 10 to 100 nanometer, and these lamellae can stack up, and between these lamellae are the amorphous polymers. And so that is what we think about semi-crystalline microstructure. Okay, there are a whole lot of other polymers where such structuring is not possible, and we call them as a glassy polymer or amorphous polymer. Now, this internal microstructure, whether it is crystalline or amorphous, has a lot to do with the mechanical properties that these materials exhibit. Okay, so these internal structures or microstructure are modified based on either the chemistry itself can dictate. If you have a chain that is very regularly placed, more symmetric, it nicely forms a packing, and then you get a crystalline polymer. On the other hand, if you have a more irregular chemical groups along the backbone, packing is not very efficient, so you get mostly amorphous structures. So from a molecular point of view, you can think about whether it can form a crystal or not. Then on the other hand, there is also processing conditions. Okay, so there are extrusions and applying strain, stress. There are external force can be applied to actually manipulate how microstructure forms. Okay, so these are the two methods by which we can modulate, control the internal microstructure, thereby the properties. Then we also talked about when you have a blocker-polymer, you can have microdomains, segregated microdomains embedded into the amorphous background, so which can also act as a reinforcement. Okay, so the microstructure and property, these are very strongly related, right? And then as a consequence of these, we also saw that the thermal behavior are also quite different. So there are temperatures called glass transition temperature that says how when a polymer goes from a brittle to a ductile or from a glassy to rubbery state, we say that is a glass transition temperature. Okay, so that's a characteristic of many polymer systems. Then if you heat further, there is a temperature where you can actually melt the polymer from a solid to a liquid. Okay, so we call this a melting temperature. Unlike regular metallic solids, which has a very unique melting temperatures, polymers do not have a very unique melting temperature. Usually they melt over a range of temperatures. These range can be tens of degrees Celsius or 20s of degrees Celsius. Okay, and these variations comes because the inhomogeneity in the molecular size, the chains are very different, the chain lengths are quite different during the synthesis, or maybe the crystals that are formed are not very perfect. Okay, so because of this inhomogeneity in the molecular size as well as the packing, you have structures that are melting over a range of temperatures. Then there is another temperature called degradation temperature. That's a temperature where you can actually break the bonds and fragment the entire chain into smaller pieces. So usually you don't want to use your polymer under degradation temperature because it's not going to be functional anymore. So depending upon whether you have a crystalline polymer or a amorphous polymer, there is a range of temperature you can use them. Okay, there is a temperature at which you can make them, you can mold them, usually above the melting point, but then when you actually put into use, usually you do it much below the melting points. Okay, so those are the broader set of discussions we had in the last class. So we'll go further in this topic and think about let's say when we make a polymer, when we produce a polymer, how do we characterize them? Okay, so this is a very broad field. Newer techniques are coming up, but we will probably touch only some of the basic, commonly known, well used techniques, okay, to characterize the physical aspect and chemical aspect. So that's the context of today's lecture. So now the most important thing is the distribution of molecular weights. Okay, so as you know, molecular weight is basically something we say for any given compound, we say how many grams per mole of a substance. Okay, 1 mole is based on Avogadro principle, we know 1 mole consists of 6.023 in 10 to the 23 number of molecules, right. So in if I take 1 mole of substance, what is the weight of that? That's molecular weight. Okay, so we know molecular weight are simple compounds like carbon dioxide, water, ethanol, methanol, you know, we know that. Now we can also define same quantity for a long chain molecule like polymers. Okay, so when we think about this polymers, how do we make polymers? What are the reactions involved? What kind of reactions are involved in polymerization? Addition polymerization and condensation polymerization, right. So in addition polymerization, what happens? Monomeric units add up, so that the number of atoms in the repeating units of a polymer is same as that of the number of atoms in the monomer. Whereas in the condensation, what happens? Usually there is a release of some small molecule like water, ammonia and other things, right. So that means if I count the number of atoms in the repeating unit of a polymer, it's going to have less number of atoms than the monomers involved. Okay, so those are broader classification. So whether you do addition polymerization or condensation polymerization, each chain will grow differently. Okay, and depending upon how you conduct them, you can have a distribution of chain lengths. Okay, so each chain may have a different number of repeating units, different number of monomeric units, meaning different chain lengths. Okay, now in any sort of that polymerization process, you are going to make a mixture of polymer chains of different length, right, and this is what we call as a molecular weight distribution. It's not going to have one single molecular weight, like for example water, 18 gram per mole, there's no uncertainty about it. But when you say polymer, you can't assign one molecular weight, it will have a distribution of molecular weight depending upon how you make them, right. In the usual unit system for small molecule, we use grams per mole, grams per gram mole as the units of molecular weight. But in polymer literature, we use this terminology called Dalton. Okay, Dalton also means 1 Dalton means 1 gram per mole. Okay, so here I have given an example of the distribution. On the y-axis, we have number of molecules having a particular molecular weight. If you look at this curve 1, you can see that this is the peak value, and then you see there is a very broad distribution. That means there are chains that have very small molecular weight, that means very shorter chain. There are chain that could be very long, having very large high value of molecular weight. Okay, so a typical polymerization synthesis will give you this kind of a distribution. Okay, if you compare this curve 2, the curve 2 and curve 1 have the same peak value. Okay, the molecular weight at which it peaks are the same, but then if you look at the spread, you see that this curve 2 actually is a little bit narrow, whereas curve 1 is more broad. Okay, so distribution can be very broad, or it can also be narrow. And if you look at case 3, this also has the same value at the peak, but then you see there is a larger fraction of molecules in the right hand side of this peak, meaning this distribution is skewed towards high molecular weight. Okay, there are fewer short chains and more of long chain molecules. So any of this is possible. Okay, you can have a very broad distribution, narrow distribution, sometimes skewed to the right high molecular weight, sometimes skewed to the low molecular weight. Okay, so these are all different possibilities, and there is a lot of discussion going on how to make this distribution narrow, as much as narrow as possible, because narrow means all chains are going to behave identically. If you have a very broad distribution, the small chains will impact some way, the long chain molecule will impact differently. So the property of the mixture is going to be determined by all the fractions. Okay, so the key aim here is to conduct the polymerization reaction so as to get as narrow as possible. Okay, which we call them as a monodispersed polymer polymers, okay, all having almost same molecular weight, okay. So now the question is, let us say you conduct a polymerization reaction, and one of the important thing we want to know is how do I find the molecular weight or molecular weight distribution, okay. So there are several techniques. One of the oldest and often used common technique is called the gel permeation chromatography. In short, we call them as GPC. It is also known as size exclusion chromatography, okay. These are synonymous, gel permeation chromatography or size exclusion chromatography, right. And if you see how it works, it is a very simple experiment. You basically have a column, okay, and this column will have some packing, okay, packing with beads. So if you are a chemical engineer, we have studied about this packed bed reactor, packed bed columns, right, which is used for giving good gas liquid contact, okay. This is also something similar, but these packings are little different. These packings are very porous, okay, with a very well defined pore sizes, okay. So the idea is you take a hollow cylindrical column and then you pack this column with a set of porous particles, okay. So then what you do is you inject a mixture containing polymers of different molecular weight. For example, in this case you see there are dots colored red, green and blue and gray. The gray ones are the packing material which are very porous. So if you look closely, this gray particle will have this many of these internal pores, okay, and the pores are not shown in these things, okay. It is shown as just a gray sphere, but if you look closely, these packings will have very tortuous pores shown by this in this figure. So when you try to inject a mixture of polymers of different chain length, different molecular weight, okay, which is shown by colors of red, green and blue, okay. The red ones are polymers with a smaller size. It is supposed to be a chain like, but here for illustration we are showing as a sphere. Imagine that is a polymer with a smaller molecular weight, and the green one has a moderate and the blue one has the highest in this particular mixture. So when you inject these mixture of polymers at the top of the column, as these molecules pass through, there is going to be a carrier fluid that is going to carry them along. So as these molecules go through, what will happen is the smaller molecules will get a longer path to travel because they will go through the pores and then come out, whereas the bigger ones will not enter the pore, they will straight away come out. So if you look at the bottom of this and find out who is coming first, you will see the biggest molecules will come first because they are not trapped inside the pores. They do not go through the pore, they come outside the surface through the macropores. So they will come first. So you see that the first signal, if you look at the concentration of species coming out, the first signal will come because of the biggest molecule. Then comes the moderate range, that is the green one. The last one would be the smallest one because the smallest molecule would have gone through many of the pores, tortuous pores. It actually remains, the retention time, the residence time of the smallest molecules are longer. So they will come last. So that means by looking at the time of arrival of these molecules, we can relate the molecular weight, right. So this kind of signal is very similar to how we do RTD analysis in a plug flow reactor. In a plug flow reactor, we put a small pulse dye input, and then you look at the response of this pulse. Depending upon the flow condition inside, you will see a very similar kind of signal that you put, or it can become more dispersed depending upon what is the hydrodynamics inside. So here, instead of putting a dye, we are putting a mixture of polymers of different molecular weight, and the time the molecules spend inside the column depends on the size. The smaller ones spend more time, bigger ones spend very less amount of time, okay. So typically you get this kind of chromatograph which shows this retention time versus the signal. And usually what we do is we have a standard, we have a calibration, I will show in the next slide, and then you match the calibration with the standard calibration with the sample. From there you can say if the retention time is this, what should be the corresponding molecular weight, you can relate. So in this technique, one of the key thing to find out is choosing this stationary phase and mobile phase. The stationary phase is nothing but the packing, the beads that are packed. The mobile phase is the solvent which carries these molecules along as a carrier fluid. Okay. Now, this you can do for both hydrophilic polymers as well as hydrophobic polymers. Any example of hydrophilic polymers? Which polymer dissolves in water? PVA, okay, polyvinyl alcohol. What else? PG, PU, dextran, right? And many proteins. So these are, so there could be polymer molecules that are water soluble, and there are other molecules which are not water soluble, but they are soluble in non-polar solvent. Example, what are non-polar organic polymers that will not dissolve in water but in non-polar media? What is that? Yes, polyethylene, polypropylene, PET, right? These are all organic polymers. You need a organic solvent to dissolve them. So, if you have a non-aqueous polymer, that is polyethylene, polypropylene, polystyrene, etc., right? What do? You actually dissolve these polymers in a solvent, which are THF, toluene, xylene, etc. Okay. So, this forms a mobile phase, that is a carrier fluid that will carry the polymer through the column, whereas the stationary phase, which is a packing for these kind of non-aqueous phase, would be polyester and styrene divinyl benzene based beads. These are beads made up of styrene beads and polyester beads, and the beads should be such that it should not absorb the polymer. It just only allows a path through which it can go through. It should not retain, it should not absorb. Okay. So, therefore, selection of a mobile phase and a stationary phase for a given polymer is little tricky. Okay. It is not very well known. So, you have to do a little bit of a trial experiment to find out what is the right set of mobile phases and stationary phases. Similarly, when I have an aqueous system, that means water soluble polymer, right. In this case, you will think of a mobile phase as something water soluble or polar, which involves methanol, dimethyl fluoride, acetonitrile plus some water. Okay. You take a mixture of water plus any of the solvent, and then you dissolve the polymer, that forms the mobile phase. And here the stationary phase is typically beads that are made up of silica gel, glass and dextran and so on. So, okay. So, there are commercially available stationary phases, you can just buy them. Okay. It is just that you have to know for a given, you can use this for water soluble as well as water non soluble polymers. For a given polymer system, you should know what are the mobile phases and stationary phases you should use. So, I was mentioning about this calibration. Okay. So, before you do the sampling, before you do this size exclusion chromatography or gel permeation chromatography, what you need is you need standards. You need to have polymers of the same chemistry or similar chemistry having well defined molecular weight that you could have done from some other measurements, viscometry or Maltitov and other kind of measurements. So, using the standards, you will actually find the log of molecular weight versus the retention time. Okay. As you can see that as the molecular weight increases, the retention time becomes smaller. That means, larger molecule will have a shorter retention time, smaller molecule will have a larger retention time. So, this kind of a standard graph has to be first made. Then, when you do the actual sample, you match the retention time, from there you can read out what is the molecular weight. Okay. And typically, the output of this gel permeation chromatography will have this kind of a curve which shows a distribution of molecular weight. Okay. So, the higher, so this end is the higher molecular weight and this is the lower end of the molecular weight. Okay. This is the time which is called elution time or retention time. So, when you start from here, the first few of them would be the high molecular weights, and then you see large fraction of molecules are in this particular size range, and then there is no molecule in this size range, and then there is a low molecular weight chain. Okay. So, you basically can get the entire molecular weight distribution information from this gel permeation chromatography. Okay. And it depends on the availability of the calibration with standards. Any question at this point? Anyone has done this? Gel permeation you have done? With what sample? Can you tell me this mobile phase, stationary phase? So now, since I mentioned that there is a distribution, we cannot all the time show the distribution curve. We need some sort of a statistical quantity to represent the distribution. Okay, so here we define certain average molecular weights. At least we use two of them. There are many kinds, but at least two of them are very, very important. One is something called number average molecular weight, shown as Mn. This N here means number averaged. That means you count the number of polymer chains of given molecular weight and then you average them over based on the weights. The other one is called the mass average or weight averaged molecular weight. So here you are not looking at the number of chains, but you are looking at weight of each chain, the mass of each chain. Okay, so you can see this is a simple number based weight average, number based average. Then this equation gives you the weight averaged molecular weight. So the way we do this is, so here I equal to 1 to n. So you basically sum over all population that you have, and if each population has a particular number of chains having a particular molecular weight, and then you multiply the number and its molecular weight and divide by the total number. So that would be a number average. Whereas in the molecular weight average, in the weight average molecular weight, you basically multiply the weight of each chain with its molecular weight, sum over, and then you divide by the total weight of the polymer. Okay, so these are very commonly used statistical quantities. So these are only going to tell you about the mean values. Okay, so here when I have this kind of distribution, okay, when I apply those formulas of number average or weight average, I am going to get one single number. That single number may actually refer to average molecular weight or the mean molecular weight. We also define something called degree of polymerization. It is an indication of how many repeating units are there, how many monomeric units are there in the polymer chain. So this is defined as number average molecular weight divided by the monomer molecular weight, the weight of the monomeric units. Okay, so it's an indication of, so dp will be, it could be like thousands, 10,000 or maybe 1 million. That means that many number of repeating units are there in the polymer chain. And another important quantity is called this polydispersity index, PDI, which is defined as a ratio of weight average molecular weight to the number average molecular weight. If you have exactly monodispersed polymer, all chain having the same number of repeating units, same mass, then the polydispersity index would be just 1. So that would be highly monodispersed, all identical chains. But in practice, it's not going to be this. It's also going to be, PDI is always going to be more than 1. Okay, so that kind of indicates, you can imagine this gonna gives an information like a standard deviation. Okay, so mean is given by the number average or weight average, and the distribution is given from the polydispersity index. Yeah, so if you have a you can define, I think you can define a degree of polymerization for each block if you like. Okay, or you can take an average weight of the monomer and then use this if you have a more than one monomers. Okay, so here is an example just to illustrate this, the formula and how we go about finding it. So let's say we have a two monodispersed sample A and B. When I say monodispersed sample, what I mean is there is population A and population B. They basically are same kind of polymer, but A has a particular molecular weight and B has a particular molecular weight, but A has all of them same chain length. B also have all the same chain length, but they are two different populations. So the molecular weight of this population A is 200,000 gram per mole or Daltons, and of B is 400,000 gram per mole. Now let's say you take 2 grams of A, polymer A, and 1 gram of polymer B, and then you blend it. So now you have actually artificially made a binary mixture. Okay, so to start with, A was monodispersed, B was monodispersed individually, right? For them, the number average, weight average, PDI are equal, and PDI is 1 for both of them separately. But now you take 2 grams of A and 1 gram of B and you make a mixture. Now this mixture now has a two kind of distribution, right? One that is 200,000, another is 400,000. But now we want to look at the average, number average, weight average, molecular weight for this mixture of A plus B. So I go to this definition of number average, and here I have only two populations. So N is equal to 2. So first I write NAMA, that is number of moles of, number of chains or number of moles of component A times its molecular weight plus number of moles of component B, its molecular weight, divided by the total number of moles, right. So that's basically I am just expanding the summation for two species here. If you have more than two species, you will have as many number as you have. So here to get this number of moles of A, I take the weight, which is 2 gram, and then I divide by its molecular weight. So I get so many number of moles, right. You can keep it in moles, or if you want to convert it in number, you can also multiply this by Avogadro number and get number of chains also. Okay. Similarly, for NB, you have 1 gram of B divided by its molecular weight, and you have so many moles of B. So number of moles of A and B are calculated based on its mass and its molecular weight, right. So then what you do, you basically go and substitute in here. So here we have Na times its molecular weight, that is 2 into 10 power 5, plus this is NB times its molecular weight, which is 400,000, divided by this is Na and this is NB. When you put all this together, you will see that the average average molecular weight of this mixture is about 240,000 grams per mole. Now you can also calculate the weight average molecular weight, in which case you are going to use weights, not the moles. So that is straightforward, because we know that A has 2 grams, its molecular weight, B has 1 gram and its molecular weight, the total weight is 3 grams, right. And then if you put them all together, you get 267,000 gram per mole. Clearly you can see that these values are not the same. Okay. So the weight average and number averaged molecular weights are not same for polydispersed samples. It's only equal for monodispersed samples, right. So now you can also calculate the polydispersion index, which is the weight based average to the number based average. So you get something like 1.11. So typically we represent this as 11% polydispersity. Okay. Any question in this example? Do you see how this is done? Okay. So, a little bit of a recap. So we are saying that polymers are synthesized through polymerization reactions, addition, condensation, and this will lead to a distribution of chain lengths. That means there is going to be a range of molecular weights. There is a distribution of molecular weights. So how do we measure these molecular weights? We use what is called this gel permeation chromatography or size exclusion chromatography, which is a technique that separates compounds based on its size, because it comes through some sort of a porous path. Smaller molecules take more time, larger molecule takes less time. Based on the elution time or retention time, based on some calibration curve, you can relate the retention time to the molecular weight. Now once you have the distribution, we don't want to work with the distribution all the time. We have to define some statistical quantities to represent the distribution. Most commonly used statistical quantities are number averaged molecular weight, weight averaged molecular weight. Okay, we saw how to calculate them. And then you can also define something called degree of polymerization, which illustrates how many number of repeating units are there. And then polydispersity index, which is a ratio of weight average to number average molecular weight. It captures the polydispersity in this system. Polydispersity index of 1 means it's a monodispersed sample, right. Now there are so many other techniques to do this molecular weight calculations, molecular weight distributions, but we will only confine to size exclusion because that's very commonly used methodology. There are viscometry methods, there are other methods one can do. So now moving on, I want to spend some time on thermal analysis also. So as we already mentioned that the polymers are crystalline, amorphous, they have got glaciation temperature, they got degradation temperature, they got melting temperature. So how do we measure these transitions? So again, several techniques are possible, but the most important ones are what's called this differential scanning colorimetry. I mentioned this in one of the previous classes, and what kind of information we get from them, and also something else called gravimetric analysis. Okay, so these two are very simple but very powerful techniques to give us information about the thermal behavior of polymers, right? So let's look at both of them in detail. Now, the differential scanning colorimetry, in short called DSC, basically the way it works is there are basically two sample holders. Okay, there are basically two holders. In one holder you will put the sample, in the other holder we will keep a reference, some reference material. Okay, and these two sample holders are thermally isolated, there is no thermal contact between them. Okay, and both of them are heated by a resistive heater. So you send current to a resistive heater and you can heat the sample. So typically you would put a few milligrams, maybe up to 5 to 50 milligrams of sample in the test holder. So the T here means thermocouple, it measures the temperature of the sample. The H here means it's a heater. Okay, so a current is sent to this heater to actually provide resistive heating. The same thing for the reference sample holder. There is a heater to heat the reference sample. There is also a thermocouple to measure the temperature of the reference. So what generally happens is that you try to heat the sample in a linear fashion, 10 degrees per minute, 20 degrees per minute, or 5 degrees per minute. You decide heating rate. Okay, so based on this, current will be passed to the heater, and then the temperature is measured for both. So generally what happens is we try to adjust the current such a way that the temperature difference between the sample and the reference is nearly zero. Okay, and then you look at how much current is passed. From there you find out how much energy is absorbed by the sample. Okay, so typically we express, since we are heating as a function of time, we express millicalorie or millijoules per second as a heat that is given to the heater. Okay, and then you record this as a function of time and power. Okay, it's a very simple setup. So all we are doing is we have a sample, we have a reference, we heat them at some linear profile and find out how much heat is supplied to this sample, so as to keep the temperature difference between the two being 0. Okay, so if you look at this output, typically you measure this is milliwatt, that means millijoules per second is milliwatt. In the x-axis we have temperature, or sometimes you can also put time here, because time and temperatures are linearly related. As I said, this is heated by a particular linear heating rate. For example, in this experiment, the sample is heated 10 degrees per minute. Okay, so when you heat it, what happens? Time is elapsing and the temperature is also increasing. So here temperature versus heat flow is plotted. You can also plot the same information, heat flow versus time also. Okay, because the heating rate is constant, time and temperatures are related here. So then you would actually get signal something like this. Okay, so there can be very small increase and then there can be a very rapid increase and come down. Okay, so typically when you have a semi-crystalline polymer, you will see this kind of a very sharp peak indicating absorption of heat to melt the crystals. Okay, so whenever you have this kind of a homopolymer, semi-crystalline polymer, if you do DSC, you will see this kind of a signal which shows a very sharp peak. Okay, so the area under this curve is actually proportional to the heat of fusion. We can actually use this information to find out the degree of crystallinity in the sample. Okay, so the degree of crystallinity is the heat of fusion divided by the enthalpy of fusion of a completely crystalline sample. Okay, and multiplied by 100. So this heat of fusion is obtained by taking area under this curve. So as you can see in this example, the area under this curve, which is a heat of fusion, is 228 joules per gram, and then corresponding to the pure 100% crystalline material, the heat of fusion is 286.2. So from here you get a crystallinity of 80%. So DSC is a very powerful technique to find out what is the extent of crystalline nature of the material. Okay, If you have another sample with a lesser degree of crystallization, you will see the peak is not as pronounced as this, it can be more shallow or shorter. Okay. So, DSC is a very powerful technique to measure the crystal content, the amount of crystalline domain in the polymer, okay, using this kind of a thermal scanning. Another application is to find glass transition temperature. There are some polymers that exhibit glass transition temperatures, and you can also find that by looking at a small jump in this. Okay, this is, as you know, Tg always smaller than the melting temperature. So, we have not really gone to a melting stage here, we are looking at a shorter temperature range. So, here is an example of acetonitrile butadiene styrene rubber, ABS. Okay. So, it is a copolymer. You got acrylonitrile and then butadiene. So, you can see that there is 1 Tg of minus 84, that is due to the butadiene part of the polymer showing a glassy behavior, glass transition behavior, and at 110 the other part, which is acrylonitrile and styrene polymer, showing a Tg of 110. So, even if you have a blend of two polymer, each one of them will have its different glass transition temperature, and you can actually detect both of them using a DSC. Okay. So, DSC is very powerful to get Tg, melting temperatures, also the degradation temperature. I do not have an example here, but if you heat further, you will see heat absorption related to the degradation of the polymer too, right. So, apart from DSC, this thermogravimetric analysis called TGA is also very useful and common. This is even more simpler experiment. All you do is you take a sample, you heat it to different temperature, and you simultaneously measure the mass, right. So, when you have a sample that has some volatile compound, let us say it has some moisture or some organic solvent, so that will evaporate first, that will show in the mass loss. Okay. After some time, if there is any melting, okay, so when you have melting, the mass loss will not be there. So, melting, phase change you cannot see here, but presence of filler, volatile compounds, those things you can see from here. Many times we compare DSC curve and the TGA curve together to find out what is happening in the material. Is it a phase change happening, or is a loss of some material is happening because of impurities, fillers, volatile compounds. Okay. So, most of the times if you look at thermal analysis, it will be a combination of gravimetric analysis, which is nothing but mass loss versus temperature or time, versus the DSC, which shows how much heat is absorbed or liberated as a function of temperature, right. So, the key is to find the mass of polymer, filler and volatiles present in the polymer sample. So, you see here, you see a big mass loss here in these curves. These actually refers to degradation. The polymer gets degraded and then they become volatile and they are removed. Okay. Where a small dip here is related to some sort of volatile losses, right. Now, so we looked at molecular weight distribution and its measurements, then we talked about some thermal analysis. Now, sometimes you also want to know what is the chemical details of the polymer. Sometimes we do not know the chemistry of the polymer too, the one that you synthesize. You want to double check, you want to cross check whether the polymer that you have synthesized is the actual polymer that you wanted to synthesize, right. So, we need to think about a chemical analysis. Again, there are many techniques for doing chemical analysis, but the most simple, powerful yet easy to do are the FTIR. It is called Fourier transform infrared spectroscopy. Okay. So, the idea here is, when you have a polymer molecular chain, you got this bonds and side groups, okay, and they undergo different kind of thermal motion. You can have what is called the stretching motion. Sometimes the stretching can be asymmetric, that is one bond stretches more than the other, that is called asymmetric stretching. You can have bond bending, you can have bond rocking, both of them actually synchronizing, and then there are out of plane motions, twisting. Okay, there are so many different kind of molecular vibrations at room temperature, right, these molecules undergo. And typically if you look at the frequency of these vibrations, these are very low energy vibrations, and these energies corresponds to IR range. So, when you try to shine the sample with the IR light, and whenever there is a resonance between the vibration frequency and the incident radiation of the light, that light will be absorbed. So, when you shine IR light through the sample, some energy will be absorbed, okay, and then you have a detector, you can find out how much is absorbed, how much is transmitted. So, based on this information, you can find out which bonds are present in the sample, okay. Now, if you have a reference, if you know some compound and you have already recorded the reference FTR fingerprint, you can match and then find out whether in your sample what are the chemical groups you have. So, basically you can find out the chemical groups, the chemical bond information in your sample against a reference system, okay. So, typically the IR infrared wavelength ranges between 2.5 to 50 micrometer, okay. These are much longer than the visible range, okay. Visible ranges are about 300 to 700 nanometers. IRs are much larger wavelength, that means lower energy. So, the wavelengths are typically given in terms of wave number, which is basically the inverse of wavelength. When you invert this 2.5 micrometer and 50 micrometer will become in the range of 4000 to 200 centimeter inverse. The FTR graph are always reported in terms of wave number, which is inverse of wavelength. So, as I said, in a molecule, bonds vibrate in IR frequency, and if you shine IR light, it will absorb that energy of radiation, okay. So, you can look at the absorbance and transmittance, and then you can measure it as a function of wave number, okay. And each chemical group has a distinctive IR fingerprint, and you can have standards, you can compare your sample with standards, and then you can match. So, you can see here is an example. This is how it is shown. On the y axis we have transmittance, how much light is transmitted, okay. On the x axis we have the wave number. So, you can see the range is from 4000 to some I do not know 500 centimeter inverse, okay. So, that is a IR range, and you can see that this sample absorbs at some specific frequencies, specific wave numbers. So, each of these dips, the peaks that you see are characteristic of a particular chemical group, okay. So, now usually these are not manual anymore, these are all highly automated. You put your sample, you do scanning, you get this kind of a fingerprint, then you have a database of all the known compounds FTR spectra, and then there is a software that will match the closest match to the sample FTR spectra. From there you can say whether your sample is made up of what chemical, okay. So, I do not know if you can see from there. So, this is basically the reference comparison. The topmost has the highest correlation, the regression coefficient is 0.9985, very close to 1, and that matches with 30 to 32% of acrylonitrile butadiene rubber. So, your sample is likely to be that because it matches closely. The next standard they have is 37 to 39% acrylonitrile butadiene. So, since it is a copolymer, you have a different composition. Each composition have a different fingerprint characteristics. So, now the standards have different compositions, your sample is matched against those, okay. So, the one that has the highest correlation are the one at the top, which has 30 to 32% acrylonitrile butadiene rubber, okay. So, usually you and then you can see that there are also other references. There is a plastic bag made up of polyethylene, that is standard number 15, that has a very poor correlation, it has a correlation only 0.4. So, you will always look at the reference that has the highest correlation with your sample, and you will say okay, your sample could be close to that reference standard, okay. So, that is FTIR. Again, I mean, as I said before, you can actually take so many classes for each of these techniques separately, but I want to only give you pointers of how to use these techniques to measure certain physical and chemical, physical and thermal properties. What I hope to do is, I was talking to Reshma, this FTIR DSC is something that we do routinely in our lab, okay. So, it may be possible that we can actually make our own sample, maybe we will take some sample from PET bottles, or I do not know, if you are willing to sacrifice your umbrella, take some nylon cloth from your umbrella, or whatever you like to sample. Think of your own sampling. Okay, think of something that is made up of nearly clean polymer, neat polymer. So it's better to so that it's easy to figure it out. Okay, so we will come up with a plan because time is short and getting all of you getting to do some experiment is a little bit hard, but we'll find a way. We have information of the groups names, and we will come back to you and ask you availability of your time, and maybe Saturdays or maybe later in the evenings we'll try to set up some experiment where you can do FTIR, DSC, TGA. Gel permeation chromatography we have, but it's a little sensitive instrument. I don't know whether we have access to do all of this, all of you, maybe few of you can do it. Okay, so we'll arrange that experiment sooner. Okay, yeah, okay, with that we'll stop here.